Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we're starting the next talk. I was once in a lecture by Chi Lu, and he explained that at least when we talk to the outside world, we shouldn't talk about exploration, exploitation, but about learn and earn. And similarly, instead of greedy algorithms, they should be locally optimizing algorithms. In the same spirit, we'll just, next we'll hear a talk from Miklos Racz, who will talk about sequence assembly from perturbed bow and arrow reads. Please.
Thanks, Yuval. My mom really loves this new title. So I'll be talking about joint work with Shirshendu Ganguly and Elchanan Mossel. And so the motivation is DNA sequencing. DNA sequencing has really revolutionized the biotech industry in the past couple of decades because the DNA sequences of organisms contain so much information about them, and there are tons of applications. Unfortunately, we cannot just read the DNA sequence of an individual from left to right. That would be great. But the current technologies, what they allow us to do is to get a bunch of short or not so short substrings of the long sequence that you're interested in. Okay? So X is the DNA sequence. And so this is just a sequence composed of A's, C's, G's, and T's. And what you get is a bunch of short substrings, which are called reads. So the problem we are facing is to reconstruct this original sequence X from the reads R. Okay? So there are a bunch of sequencing technologies that have been developed in the past couple of decades. And basically, what ideally we would like are long reads that are error-free or have very few errors. However, this is hard to achieve. So typically, the types of technologies try to trade off these two desirable in these two quantities. So really, originally Sanger had developed a type of sequencing which was unfortunately very expensive. So what really brought DNA sequencing to widespread use was the development of next-generation sequencing methods, such as Illumina, about a decade or so ago. So this allowed to get high throughput data really cheaply. Unfortunately, in order to get really low error reads, this was restricted to having very short reads, so on the order of maybe length 100.
When you say the error, this is the error rate. It's the percent of wrong symbols, or?
Yes, yes.
And we're assuming they're kind of uniformly spread, or?
Yeah. So, kind of the point is that these different sequencing technologies have different types of error profiles. So there's some noise involved, but there are also these are some biochemical things going on. So there are some kind of systematic errors that could go wrong if not done properly or depending on how it's done. So because these next generation sequencing methods only produce short reads, it led to highly incomplete assemblies, and they were really fragmented because there were big chunks of the genome that you couldn't connect properly. So partially in order to get around this problem, the new kind of technologies that are emerging are ones that get much longer reads, so over 10,000 base pairs. But unfortunately, the current status of these still have high error rates, so upwards of 10%. So the two main examples are PacBio's single molecule real-time sequencing and the Oxford nanopore technologies. But so what we see is there are this multitude of technologies, and they have different error rates, different error profiles. And so the current assembly algorithms typically are tailored towards the particular technology that is used to produce the reads. And of course, this has a good side, right? Because if you're using a particular technology, you want to really you want your algorithm to exploit what's going on there. But on the other hand, these technologies are evolving at a rapid rate, and so in 10 years from now, we're probably going to have different technologies, and the question is, will this same algorithms be good, and how much of the tailoring to one particular technology will make it unsuitable for other types of technologies. So we'd like to understand what are the type of general robust reconstruction algorithms that can work well with respect to different sequencing technologies. So in order to study this, what we're going to do is not commit to one particular error profile, but instead we'll study an adversarial corruption or error model for the reads. Okay? So what we assume is that instead of getting a true read R, what you get is a corrupted read. Or what Yuval, what was your phrase? I forget already. Perturbed. Yeah, you get a perturbed read. So the types of errors that happen are deletions, insertions, and substitutions. So here in this example, these two A's in red got deleted. This yellow G turned into an A, and this C in green was inserted in between the G and A. Okay, so these are the typical type of errors that happen. And so the edit distance is a distance that quantifies how much of this errors happen. So the edit distance between two sequences is the minimum number of insertions, deletions, and substitutions required to take one sequence to the other. So the only thing we're going to assume is that we know that the edit distance of the perturbed read is at most something from the true read. Okay? So in particular, we're going to assume that the edit distance is at most epsilon times the length of the true read, which I'll denote by capital L. Okay? So this means that an epsilon fraction of the read can be arbitrarily perturbed, corrupted. OK. So given this error model, here's the approximate reconstruction problem. So we're going to model our sequence of interest x as a uniformly random sequence from this 4-letter alphabet of length n. So of course, this is not realistic, but this makes things simpler. And you can study this problem for arbitrary sequences. And so I'll mention some thoughts along those lines later. But for simplicity, let's stick to the simple setting. So then, once you have this sequence x, you draw reads, capital N many reads. So what this means is that you just pick uniformly at random positions along the sequence, and then you look at a substring of length L there. And then there's some adversary that can apply any perturbation they want up to a fraction of epsilon of the read length. And then we're given this set of corrupted reads. And our goal is then to approximately reconstruct the original sequence x. OK? So our algorithm will output some sequence x hat, not necessarily of the same length n, because we don't even necessarily know what that is. And what we want it to satisfy is that it have a close edit distance to the original sequence. So because of this adversarial error model, you cannot really hope to get smaller than linear in epsilon n, right? Because, for instance, what the adversary could do is, so here's your sequence, and you chop it up into length L parts, and then it says that I will never give you this information. So here, these are of length L, and this is of length epsilon L. OK? So then an epsilon fraction of the whole sequence is just not given to you. So you cannot really do much better. So what we want is some algorithm that gives you a small constant factor approximation. OK? Are there any questions about the setup?
Do you know anything about random error model? Like if the errors are randomly?
Yeah, so if the errors are, if you just have IID noise, then there are results that say that then you can average them and you can do well. Yeah, I'll refer to that a little bit later.
But it's, I mean, it's somewhat realistic that the errors might be not just IID, right? Because it sort of depends on the sequence, you know,
yeah.
what goes wrong.
Yeah. OK, so this problem, I mean, not this particular problem, but the general problem of reconstruction from reads has been studied a lot over the past several decades. And so the two main obstructions to reconstruction are very well known. So the first is that if your reads are too short, then this will lead to repeats, and then this will lead to ambiguity in reconstruction. So let me explain in more detail what I mean by this. So suppose you have a substring A here that repeats in the sequence, and also a substring B here that repeats, and that your reads are shorter than the length of A and B. Okay? Then, suppose you had all the reads, even then you wouldn't be able to distinguish between the sequence at the top, where Y is on the left and Z is on the right, and the sequence at the bottom, where Z is on the left and Y is on the right.
When you get the reads, there's no ordering of where they come from?
No. They're just, they're just in a bag. Yeah. So somehow the technology that gives you this is that you create a bunch of replicas of the DNA sequence, and then you put it into this big soup, and you blow it up, and you get out these reads. That's roughly how it goes. OK. So your reads have to be long enough. And the other main obstruction is that you have to have enough of them to cover the sequence. So again, if there's some part of the sequence that you have no information of, then you have no way of reconstructing what's there. And also, you don't know even if you could reconstruct everything on the left and everything on the right, you don't know whether which is on which side. Okay.
Why are you giving them credit for coupon collector?
Yeah. So this is essentially a coupon collector problem, but OK, in this setting, they were the one who did this. But OK, they also applied it. They applied it to real sequences and computed these various quantities and things like that. But yeah, so this is a coupon collector problem. This is the number of reads you need in order to cover the sequence with probability at least 1 minus delta.
I must have missed this on the slide that gave your model. The reads are selected from uniformly random locations.
Yes.
So the adversary only enters when the corruption process.
Yeah, exactly. Yeah. Yes. So this first obstruction goes back to Conan, and this goes back, to wherever it goes back to.
Coupon collector.
Yeah, the coupon collector. So yeah, and this is often referred to as the repeat limited regime, and this is referred to as the coverage limited regime. Okay, so if epsilon is equal to 0, so you have error-free reads, then this problem is the same as you want to reconstruct the sequence exactly. And so this has been studied in various settings, in particular in this exact setting where you have shotgun sequencing and a random string. This was studied recently by Motahari, Bressler, and Shea, who showed that these are the only obstructions to reconstruction. Okay. So more precisely, if X is a random sequence, they do more than that. It's more general, but let's stick to this simple setting. and the reads are logarithmic in n. So if you have a random sequence of length n, then the longest repeat will be on the order of log n. Okay? And let's suppose the error probability that the probability that the algorithm is correct, you want that to be at greater than 1/2. So then, if the reads are shorter than this threshold so that you do have repeats in your random sequence of this length, then exact reconstruction is impossible because of the aforementioned fact. And if you're above this threshold, so you don't have repeats, then basically, if you have enough reads to cover the sequence, then you're good and you can reconstruct. So the ratio of the minimum number of reads you need and the minimum number for reconstruction and the minimum number of reads you need for coverage goes to 1. Okay? And so they looked at also a more general model. So the sequence can come from a Markov chain, for instance. And of course, for the real-life application, you also are interested in arbitrary sequences. And for arbitrary sequences, so Blesser, and Shea studied this problem, and they showed thresholds based on the repeat statistics of the sequence. So it's very natural, right? For a random sequence, you know what the repeat statistics are, so you can get explicit thresholds in this way. OK, so an approximate reconstruction, so basically the result is that you can do approximate reconstruction if you have enough reads and if the read lengths are long enough. So the reads are long enough. So more precisely, so this is a bit of a mouthful, but basically you can get an approximation factor of anything greater than 3 if epsilon is small and the read length, the reads are long enough, again on this logarithmic scale, and you have enough reads. Okay. Okay. Let me make some comments. So I'll show in a second that the simple sequential algorithm works, right? And that's good because that's kind of the most natural thing you might expect to do. You just patch the reads one by one. So here in the statement, I have some dependence on epsilon of the required read length and the number of reads. So this is not necessary if you just want a finite approximation factor, but I won't get into this. One thing I should mention is that, so in the previous picture, when epsilon is equal to 0, then there's this very nice picture of a clear, sharp threshold. And so this was made easier by the fact that in that case, there was just, you either reconstructed the sequence exactly or you didn't. So it's a binary thing. Here, the measure of success depends on this approximation factor. So it's not something that is binary. So it might be the case that the best achievable approximation factor depends on how many reads you're given and how long they are. Okay, so there might not be such a nice picture. So we would like to understand this picture better, but OK. Let me just mention related work. So people have looked at various noise and error models. So in particular, Motahari, Ramchandran, Shea, and Ma looked at exactly this setup of just adding IID noise. And then you can imagine that averaging out this noise, so you can average out this noise because of the coupon collector fact that once you have coverage, most places are actually covered log n many times. So you have many reads covering each coordinate. So if you have some amount of noise, then you can still deal with that. And Shomoroni, Kurtad, and Shea looked at an adversarial model, but it's a somewhat weak adversarial model. So I can explain more offline.
If you just wait a constant multiple of the cover time, then everything is covered log times.
Right. Yeah. OK. So before just showing you the algorithm very briefly, let me say that, so in order to analyze the algorithm, so the only assumption we're making is how the edit distance can change. So what we really need to understand is, what is the edit distance of two reads that don't overlap, and what is the edit distance of reads that do overlap, and how it depends on how much they overlap by, right? Because the adversary can change things in edit distance, so this is something we really need to understand. So the picture is the following. So if you take two independent sequences of length m, then their edit distance will be linear in m. This just follows because of the subadditive ergodic theorem. So there's going to be some limiting constant here, and it's a hard problem to determine this constant explicitly, but empirically you can simulate this and find what in particular when you have 4 symbols, this constant is about 0.51, and using a volume argument you can give a lower bound of 0.33. So this means that if you have two reads that don't overlap, then they're pretty far apart in edit distance. So if the adversary can only change the edit distance by a little bit, then they'll still be far apart. The other end of the picture is when you have two reads that really overlap by a lot. So let's look at this picture here. So the edit distance, if they overlap by a lot, then the edit distance is at most twice the shift between the two reads, because you can get from this read at the top to the one at the bottom by deleting the blue part on the left and adding the red part on the right. Okay? And for random sequences, so it turns out that this is exactly the edit distance. You can't do better than this because of the randomness of these sequences. And this is true up until a constant fraction of a shift between the two sequences. And this empirically, it's true exactly until half of this constant here. And then the edit distance just becomes as if they were completely independent. Okay? And so, we cannot prove this curve, but we can prove that this is true until some point here, and then we have a lower bound of that form, and that tells us that if the two guys are close, then they overlap by a lot, then they're close. So the adversary cannot make them really far apart in edit distance.
So you don't know to prove that the profile has these just two lines.
No. Yeah. Okay, so I'm almost out of time. So let me just very briefly say what the algorithm is. So you take a read, and then you look at an appropriate length suffix, and then you look into your bag of reads and try to find a read that has a prefix of that length that is really close in edit distance. And so there are a couple of things you have to guarantee. You have to guarantee that, so this is larger than 2 epsilon L, because otherwise you can get rid of the overlap. You also have to make sure that this is larger than the length of the longest repeat. So there are a couple of things you have to take care of, and that's why we have the various assumptions on the read length and the number of reads. But then you make, at each step you make a gain that's linear in L, and in particular if epsilon is small, then it's almost L. And you only make an error of about 3 epsilon L. Okay?
So even computing edit distance is hard, isn't it? So how do you...
Computing edit distance.
What's the complexity of it?
It's n squared.
Okay, n squared.
Okay, so let me just conclude that. So here we've introduced an adversarial model for approximate for the read errors, and we showed that approximate reconstruction is possible using a very simple algorithm. And there are challenges. So we would like to determine what are really the fundamental limits of this approximate reconstruction. Also, we would like results for arbitrary sequences, and they would be roughly of the form of saying that, well, if the reads are long enough so that non-overlapping reads have large at a distance and overlapping reads have small at a distance, then you'll be able to do it. So this is the type of result that should be true. More generally, I feel like, of course, the models where you just have pure noise, those are not realistic. But this is also a bit going overboard because, of course, nature is not necessarily adversarial. So I think there's a space for models in between previous models and this current one, and trying to find a good model in between. So in particular, we can talk about heterogeneous error rates, for instance, and various other things. So with that, let me just conclude. Thank you.
Any questions? Other questions?
I have a really stupid question. Is DNA directional? I mean, can you tell which end of your string is which?
Yeah, OK, so I'm not an expert in this, but yeah.
But yes, you can.
You can?
Yeah.
There's a 5 trend, yes.
Yeah.
Thanks.
Don't occasionally small pieces get reversed?
Yeah, that's what they're for.
Oh yes, no, I mean if you look at the whole strand, then there's a
Right,
transcription always happens in one direction.
But if you just have one of these sections of length 100 or whatever, do you know which way around it is?
No, but I believe when you get the read, you know which direction.
Oh, I see.
So if I just gave you a sequence, you wouldn't know, but the read sequence which to my understanding does that. But I'm not an expert.
To my understanding, the two strands of the helix go in opposite directions. So when you get a read, it's ambiguous whether it's forward from the left strand or backward from the right strand, or the backward base paired thing from the right strand.
But that's maybe not.
Okay, any other questions? Maybe I have one. Can you go back one slide when you said the edit is exactly 2K? Were you suppressing a little additive error there?
No, I think
Well,
there must be some randomness involved.
so
Less than or equal to 2K?
so, I mean, less than or equal to 2K follows from the fact that this construction.
But it must be. It's random.
Yeah, with probability at least 1 minus epsilon.
I see. So it's full as big as it can.
okay. Any other questions? No, let's thank you again.